All right, I want to start us off by looking back at this phenoxynyl again. What would be a good name for the functional group here that has chlorines connected to the aromatic ring? Chlorines connected to an aromatic ring. What would be a good name for that?
Some kind of a halide.
Some kind of a halide. A benzyl halide is one connected to the benzylic carbon, which is the carbon just off of the benzene ring.
Oh, and those are not.
And these are not just off of the benzene ring, they are on the benzene ring. So rather than benzylic, we'll call it aryl. Aryl applies to being part of the aromatic ring. So aryl halide. What about this oxygen group here? Functional group? Ether. Because there's carbon on ether side. And you could say it's part aryl ether because on one side is an aromatic ring. But ether for sure. What about this carbonyl group? You remember the carbonyl? Can someone tell me what carbonyl means? This is an amide. Amide, either one. But carbonyl means? It's a specific type of double bond. CO double bond is a carbonyl. And this carbonyl is an amide. Carbonyl is not a functional group. Carbonyl is a class of functional groups. It's like how hydrocarbon, if you had said, oh, there's an aromatic ring, is it a hydrocarbon? Yes, it is, but more specifically, it's the aromatic ring. Is this a carbonyl? Yes, but more specifically, it's the amide. What about the CN? Do you remember that functional group? There's two different ways that you could refer to it.
It's not a nitrile, is it?
You can call it a nitrile, or you can call it a cyano. Those are its two names. Do you need one of the sheets from yesterday?
No, I'm good.
Okay.
Can I get that?
Yes. Anybody else? Okay, so we had been talking yesterday about finding equivalent sets of hydrogens. So I want to review this on phenoxynyl because it's a big structure, so there's a lot of equivalent sets. This hydrogen on the aromatic ring between the two chlorines, unique from the other two hydrogens. It's in a different chemical environment. It has different regiochemistry. When we're talking about chemical environment, we're talking about regiochemistry. Hydrogen between two aryl halides is different than a hydrogen next to an aryl halide is different than a hydrogen next to the aryl ether. So all three of those aromatic hydrogens are distinct. Then I have this hydrogen on the tertiary carbon. I have the three hydrogens on the methyl group. That's two more. I have this hydrogen on the nitrogen. And then I have this methyl group, which is distinct from these two methyl groups. But those two methyl groups are the same. For the same reason that we would say this is not a chiral carbon because it has two identical groups, we would say that these two methyls are identical. So that's 1, 2, and then that tertiary hydrogen again, 3 groups. So 5, 6, 9 sets. That's okay with you guys? You're comfortable with looking at these hydrogens and saying they're in different places in the molecule, and the places they're in are different from each other, and so they're unique to each other. Essentially, if you can describe its regiochemistry differently, it's a unique set. It's an equivalent set. And then we looked at the NMR spectrum for it. I feel like yesterday we thought there were maybe 8 sets. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. And on the NMR spectrum, we saw 1, 2, 3, 4, 5, 6, 7 signals, give or take, because some of these signals are a little hard to identify. You know, like this one that's just before 7, kind of looks like it has a shoulder on the left-hand side. Is that a separate signal? And then we said, despite the fact that we think we should find 9 different signals, 9 different sets, some of these signals overlap with each other. So they might be different, but still similar enough. And you're okay with that as well? That different hydrogens, different signals that just coincidentally happen to be the same. Then let's talk about chemical shift. Which of these hydrogens would you expect to find the furthest left on the spectrum? Which of these hydrogens would you expect to find to the furthest right on the spectrum? Take a look at your correlation table. Anybody needs the correlation table, let me know. That was something I didn't give you. And read that. Sammy, do you need any? Okay. What do you think?
The ones bonded to carbon would be the furthest to the right.
Okay, here's bonded to a carbon, carbon. So that's most of them except for this. Is that what you're thinking?
I imagine most of them would lean towards the right then, with, depending on what those carbons are bonded to, could adjust it.
Because yesterday we said bonded to less electronegative groups, more to the right. Bonded to more electronegative groups, more to the left. But then you look at the correlation table for proton NMR. By the way, there are many, many types of proton NMR correlation tables because nobody agrees on one way to do it. Our course lead, Ron Valcarci, has a document. You guys will find that document if you're doing the PLO on spectroscopy, the one that's at the bottom of this module. His document is several pages long just for proton NMR because it tells you where to find the signal from a CH3 if it's next to a CH2, where to find the signal for a CH3 if it's next to a CH, where to find the signal for a CH3 if it's next to an O, next to an N, next to a Cl, next to an aromatic ring. It gives you an incredibly detailed view of where you can expect to find every signal. Mine takes a much, much more broad perspective. And then there are other correlation tables that are kind of in the middle of R2, where it gives you an entire spectrum, but it's maybe just the size of the page. And it says, you might see alkane in this range, and things adjacent to aryl groups in this range, and things adjacent to chlorines in this range. That's what your textbook gives you, is a full NMR spectrum with just ranges of more specific ranges. Mine is by far the most vague and the most broad. And in my opinion, that makes it the easiest to use because it helps you just quickly narrow in on things and then make assessments based on what's present. So the correlation table actually shows not everything bonded to a carbon is equally to the right. Because if that carbon is an alkene carbon, it shows up around 4 to 6. If that carbon is an aromatic carbon, it shows up around 6 to 8. If that carbon is adjacent to something, adjacent to a functional group. And I know the groups I gave you are carbonyl and oxygen, but I'm trying to tell you any functional group. So even things adjacent to an aromatic ring shift into that functional group adjacent. Even things adjacent to an alkene shift into that functional group adjacent. But there is a little bit of nuance. Do you see how the hydrogen that's next to the carbonyl is on the right-hand side of that range? And the hydrogen that's next to the oxygen is on the left-hand side of that range? That's because the closer you are to the electronegative atom, the further left the signal goes. The closer you are, or the further you are from an electronegative atom, the more to the right you are. So things adjacent to the carbonyl are further from the electronegative atom, are further to the right. There's nuance into the way I've designed the way the molecule orients. Even with the aldehyde and the carboxylic acids, hydrogens from aldehydes are more on the right of that range. Aldehydes from carboxylic acids are more on the left of that range. So what do you expect would be furthest to the right, and can we narrow it down as much as possible? What would be the furthest right?
Talking about that group that's on the board.
Yeah, for this molecule. Which signals would we expect to show up furthest to the right?
Would be the two equivalent methyls.
Exactly. These two methyl groups are the most alkane parts of the molecule. They're bonded only next to alkane groups. And the more substituted the carbon, the further left that signal goes as well. So even this primary hydrogen, this tertiary hydrogen, shows up further left just by nature of being more substituted. By having more carbons around it, more electronegative atoms. By having less carbons, less electronegative atoms. And these two methyl groups show up furthest to the right, even compared to this methyl group, because this methyl group is adjacent to the nitrile and to the amide. So by being more functional group adjacent, shifts further to the right. To the left. Is that your left? That's your right. Sorry. By being closer to the nitrile and the amide, this methyl group shifts more to the right. So, sorry.
To the left.
You know they call it downfield and upfield? And I tried coming up with a baseball analogy for that once, but I don't know that they use downfield and upfield in baseball, and it never made sense. Downfield is further to the left and upfield is further to the right, but I'll just say left and right. Okay, so furthest to the right, I'm gonna, let's just call this like 1, and then we can say that these hydrogens are probably 2. Then I think we can suspect this methyl group is in a relatively similar place to this other methyl group by being kind of functional group adjacent. So I'm not sure which one is going to be furthest to the right. We'll just kind of say they're near each other, around 2. And then I've got hydrogen that is next to an oxygen and a carbonyl. Not only is that functional group adjacent to the ether, it's also functional group adjacent to the carbonyl, both of which shift the signal to the left. There's your left. Being adjacent to both shifts the signal to the left, which actually has a compounding effect. Being next to the oxygen shifts it left, and then the carbonyl shifts it even further left. So this signal might actually show up in what appears to be the alkene region, despite the fact that there is no alkene in the molecule, because it has that compounding effect by being functional group adjacent twice. And then we have the aromatic region, and I'm just going to call the aromatic region 4 because the aromatic region all just kind of shows up within itself, and I am not going to expect you to predict which of these signals is furthest to the left. It actually gets really complicated how the aromatic ring shields and de-shields when it has other groups on it. Do you guys remember that term shield and de-shield? What? Shielding from what? Shielding from the magnetic field of the instrument. And what is shielding from the magnetic field of the instrument?
That the groups appear to the right.
If they're shielded, the groups appear more to the right. But what is doing the shielding? What blocks the nuclei from the magnetic field? The electrons interact with the magnetic field, creating a shield around the nuclei. So the more electron density, the more shielding, the further to the right. The less electron density, the less shielding, the more to the left. And the aromatic ring does some weird shielding and de-shielding stuff. So I'm never going to ask you to predict which of these is furthest to the left. I'll leave that for your advanced spectroscopy course, if you're a chemistry major, that you'll take your senior year. Just so fun. I highly advise it. Now, I actually didn't put on your correlation table the hydrogen from amides, because I have never seen on a correlation table the hydrogen from amides. So I'm sitting here with my foot in my mouth because I don't exactly know where this is going to show up. I told you guys that OH and NH, like alcohols and amides, actually show up further to the right than you'd expect. They show up from 0.5 to 5, which is not like where the carboxylic acid shows up, and not like what you'd expect by saying the closer it is to an electronegative atom, the further to the left it goes. But the carboxylic acid is unique, and the amide might be unique as well. So I'll be honest, I'm going to leave that as a question mark because I'm not exactly sure where it's going to show up. It might be the furthest to the left. It could be the furthest to the right. Okay, so we can't necessarily get in here and assign these signals, especially with how small this spectrum is and how blurry it is. We're not going to come in here and try and assign any signals, but we understand that there probably is some stuff going on here. Actually, I think there's one we can assign. Do you see that signal around 4.6? And the correlation table tells you a signal around 4.6.
Was the 1-methoxypropane?
No, the correlation table. We're still looking at phenoxidil.
The functional group adjacent
Either the furthest side of functional group adjacent,
or the vanilla.
or it's in the alkene region. And is there vanillic alkene? And is there an alkene region in our molecule? Is there a vanillic hydrogen in our molecule? No. So even though it kind of looks like it could be right in the vanillic region, it can't be from a vanillic hydrogen because there is no vanillic hydrogen. So I think it's safe to say we know that number 3, the one that's functional group adjacent twice, is the one that looks like it might be in the vanillic region because it got shifted so far to the left. Rowan?
Didn't we say like the aromatic ring ones are 7?
Yeah, so the 3 signals, or what kind of looks like 3 signals from 6.5 to 7.5, those are our aromatics. Perfect.
So you're saying the number 3 you have up there would be more to the right than the 4, even though it's that close to carboxyl. I can't do it.
Isn't that wild? These hydrogens bonded to carbon are further to the left, meaning more de-shielded and more exposed to the magnetic field than the hydrogen that's both adjacent to an oxygen and a carbonyl. Yeah,
Is that because it's like sandwiched in there with all of the density from
these guys?
the 3?
No, because it's losing a lot of density. It has an electronegative atom there and an electronegative atom there.
But that makes it more shielded, right?
No, I mean, it's exactly where we expected it to be from the correlation table. We said it's functional group adjacent twice, so we expect it to be on the far end of functional group adjacent, furthest to the left. But why are the hydrogens bonded to carbon not close to these like highly electronegative atom groups? Why are they the furthest to the left? It actually has something to do with molecular orbital theory. The aromatic ring has a molecular orbital where a p orbital on every single carbon is in phase, which creates a ring. You know the p orbital is the lobe, shaded on one side, unshaded on the other, and that ring goes around the sphere, shaded on the top, unshaded on the bottom. And when a magnetic field interacts with electrons, it can make them spin. And in this case, the electrons spin in that circular molecular orbital. And when they do that, they create their own magnetic field, and that just causes a stronger magnetic force on the nuclei. It's a little bit of wild stuff. Think about how your alternator pushes electrons in a circle and creates a magnetic field that way and helps charge all your batteries in your car and stuff. Something similar is happening in the benzene ring. Electrons are moving in a circle, and that de-shields the protons even more. Not expected, because not an electronegative group, but explained by molecular orbital theory. All right. Complicated stuff. We're breaking it down into its most fundamental pieces. The next piece to understanding our spectra. Oh, actually, I wanted to remind us about 1,3,5-trimethylbenzene. And I want you guys to tell me which signals are produced by which hydrogens. We've got this signal to the left that's around 6.8. And we have this signal to the right. I mean, I drew that really close to each other. We've got a signal to the right that's around 2.1. Which hydrogens are producing these signals?
Would the 6.8 be the hydrogens that are connected to the carbons in the aromatic ring?
Good. This signal is produced by the aryl hydrogens because it's in range for the aryl hydrogens. And this signal? The methyl group hydrogens, which are functional group adjacent. They're adjacent to the aromatic ring, which is why their signal is not close to 1, their signal is past 2. That agrees with your correlation table saying that it's functional group adjacent. All right. Now those signals that we see on 1,3,5-trimethylbenzene are both very nice signals. We would call them singlets. They have just one peak. We notice how other signals happen to have more than one peak. If we took our instrument, our software that gave us this spectrum, we could integrate those signals. Those of you that have taken calculus, what is integration?
I don't know if we're there yet.
Oh, yikes, okay. No, that's okay. For real?
We're doing.
I guess it's the end of Calc 1. No one's gotten past Calc 1? Come on, integral. All right, how about this? I want you to integrate organic chemistry into your life. No, go ahead.
Is it something with like the area?
It is something with the area, under the curve. If I wanted you to integrate organic chemistry into your life, how would you expect to do that? You would make organic chemistry a part of every little detail in your life. That's what integrating means, right? To make entirely a part of. When we talk about integration in math, we're talking about the area underneath a curve. So we would zoom in on this spectrum, and we would start calculating the area underneath the signal. Which of these signals do you suspect has a larger area? The one on the right, because they're of similar width, but one of them is much, much higher. Now, we talked about how the y-axis is relative intensity, which means that it's arbitrary units. That's what AU means, arbitrary units. Who cares what the unit is? It's not inches, it's not intensity, it's arbitrary units. So when I take the area, which is, length times height or whatever, I have an arbitrary unit, so my instrument doesn't really know what number I'm looking for. Is it really just going to pick an arbitrary number from an arbitrary unit and give me an arbitrary area? What our instruments will do is normalize. It will find the lowest area signal, and it will say, this is 1. And then relative to that signal, all of the others will have some area greater than 1. So it will take this signal and it will say 1. And then it will take this signal relative to that and it will say 3. Now I've added something to it. I've added h. And this is how I'm always going to present it to you as well. The integration is reported as some number h. And that's because the integration is proportional to the number of hydrogens in that equivalent set, the number of hydrogens producing that signal. Are there 1 hydrogens making the aromatic signal? No, there's not. So why did it set it to 1? Shouldn't it have known better? And by it, I mean your organic chemistry professor.
It's relative.
It's relative. The computer had no idea what to set it to. So it just set it to 1 because that was the lowest area signal. But because it's relative, it's some proportion of 1 to 3. Okay, now active is going to show you the old way of integrating, where the computers wouldn't actually even give you a number. The computers would give you an integral line. They would take the integration of this, and they would say, here's the rate of change that we see. So instead, it would give you something that looks like this. 1 to 3. That's an integral line. And it is not as nice as having numbers because it's not always obvious whether the ratio is 1 to 2, 1 to 3, 2 to 3, 3 to 4. You have to kind of play around with it and guess. But anytime that I give it to you, I will give you these numbers. By the way, all of the spectra that you're looking at is real experimental data, literature data, published data. There are simulators out there where you can simulate an NMR spectrum based on what it expects the signals would be. I'll never give you those. I'll only ever give you real data. And the real data doesn't come with integral lines or with integration numbers. I always add those integration numbers on there, unless the question is asking you to figure out what integration a signal should have based on a structure given to you. So, you'll notice on, because I did it on none of them, I see. Oh, no, on the back. On the very back, you'll notice that I gave integrations. Oh, and on all of the ones that I said integrals, integration. Those have integrations. They're just very hard to see, so we'll go through them in a second. Do you guys remember what this signal is the instrument is picking up?
It's the frequency of the radios.
Yes, it's radio wave frequency light that the nuclei are emitting as they relax after the magnetic field. If I have more nuclei emitting the same frequency, then that frequency is louder. Like if I have a choir and I have 5 people singing an A chord, sorry if you're a musician and I'm not making sense. 5 people singing an A, that's going to sound different than having 500 people sing in A. I would be able to tell the difference when there's a difference in amplitude. So the height is nothing. The area is everything. You guys were asking yesterday, Is it about the height? Not at all. So I want to give you another example where we can demonstrate this.
So you could have a really wide, low one that's technically more.
Exactly. Here's 3 different signals: a low, broad one, taller, narrow one, and then kind of wide with several peaks. Rowan?
Are we still gonna see row lines on ones that
On active.
are like width though?
No, the integral line just tells you the area.
Oh, so it's not even relative to height.
No, has nothing to do with, well, actually it's height times width.
Well, yeah, but
Yeah, the integral line won't change in thickness. Is that what you're asking?
I was just like, I thought it was like based on height, so I was saying when it was wide, like how would you have an integral line?
Yeah, well, yeah, good point. When it's wide, the integral line will still give you just the height, the number of signals. So can we say which of these has a bigger area? The big wide one, although that's much shorter than this. So is the combination width times height the same here as it is here? Maybe, because width increases, but height decreases. No way to know until you get in there and get the integration. So now if you were on active and it gave you this, what would you say?
They all look the same.
They all look the same. They all have the same integration. How would we know whether the integration is 1h or 2h or 3h? We don't, based on this. But that's what I'm trying to get at, is it's not the shape, it's not the height, it's not the width, it's all of that combined. So when multiple parts are changing, you don't know exactly what impact it's going to have. Okay, so returning back to this, the best integration would not have been 1H and 3H, because we know the molecule that we're looking at has 3 aromatic hydrogens and has 9 methyl group hydrogens. So the best integration for 1,3,5-trimethylbenzene, although it normalized at 1H to 3H, the best integration is actually 3 to 9, which is proportional. Those are just proportions of each other. Because what the instrument is doing, and you guys are going to get to experience this in lab next week, what the instrument is doing is it's saying this has some integration smaller than this, and I don't know what numbers I should be using, so I'm just going to take my numbers and normalize it to say this is 1, this is my smallest integration. And relative to that, this had an integration 3 times larger. But actually the best way to prepare that for our molecule is to say 3 to 9. I will always give them to you this way, with the actual integrations and not just the smallest proportion of their integrations. Because I find this to be just more meaningful anyways. Fun stuff. All right, so I'll be honest, the ones I have in the worksheet are terrible examples. Because acetone has 6 hydrogens that are all identical to each other, so they give 1 signal. And the system is going to integrate that 1 signal and just normalize it to 1. We would have to know that we're looking at acetone to change the integration to be 6. And then this is 2-butyne, which has 2 CH3 groups, which are identical to each other. And the system would just normalize it to 1. And we would have to tell the system, integrate that to 6. We'd have to know what's going on. But notice how the chemical shift of that signal is different from acetone to 2-butyne? Because being adjacent to a carbonyl shifted it beyond 2 parts per million, being adjacent to the alkyne shifted the signal to the right of 2 parts per billion. The chemical shift was different. And then I have hexamethylbenzene, once again, 1 signal. How would the instrument know to integrate that to 18H? It wouldn't. It doesn't even have anything to balance it off of. So these are the most challenging integration examples. Terrible integration examples. Sorry. Because the instrument would never even know. But what I'm showing you is that I'm not going to trick you by saying 1H, 1H, 1H. That's the lowest proportion. I'm going to give you what the actual integrations should be. Sometimes I mess up.
So the 6 and the 18 are the number of like H's for that
Correct.
signal?
Number of hydrogens making that signal, the number of hydrogens in that set.
So if you see one line like that with the 6H, and for some reason, well, I guess going the other way, if you see just the molecule and there's 6 like hydrogens, then you would know that it would only produce 1 signal, and then that would be labeled 6H.
Yes. If I knew I was analyzing acetone, and I know it's only going to give me 1 signal, and I know that 1 signal is from 6 hydrogens, then I can take the software and tell it, make it 6. Okay, here's some fun things that we can learn about a structure from integration. Oftentimes, a 3H tells us that we have a methyl group. Obviously, that's not always true because in the example above, we have an integration of 3H. That is not from a methyl group. It's actually from 3 equivalent CHs. If we see something like 6H, then we can expect to find 2 equivalent CH3s. If we see something like 9H, then we can expect to see something like 3 equivalent CH3s. Right?
Yes, but in the ring, it's different.
Well, yeah, it just, not always will 3H be CH3. But a lot of times,
Okay.
it's not always, as we just proved.
Okay.
Is your 9 sets for just the ring?
The 9H,
Yeah.
3H, 6H, 9H.
No, on the phenoxyethyl.
So we could have put the phenoxyethyl, those 3 lines at 7 together.
Oh, yeah, okay, that's a good point. In the aromatic region, I'll address this
Okay.
about the aromatic region. Just a couple of other ones. 2H often tells us that we have some sort of CH2 group, whereas 4H often tells us that we have some sort of symmetric CH2 groups. Often, I can't say always, right? These are just common things that we see. Now the real challenge is that 1H could be a CH group, could be an OH group, could be an NH group, could be a carboxylic acid group, could be an aldehyde group. Some of those we could distinguish by their chemical shift. Aldehydes and carboxylic acids show up in a very different region than everything else. But OH versus NH versus CH can be hard to know from an NMR spectrum. If it's just one H, it could be a lot of those things. Actually, I should add, much like how one H could be from a nitrogen, there is the possibility of 2H coming from a nitrogen as well. Both hydrogens are connected to a nitrogen. They're going to show up as that one signal. They're an equivalent set. Okay, I know that this doesn't look very easy to read from far away, so I'm wondering if maybe lines will help. Did that help? Okay. I like to integrate the aromatic region as just one region, essentially treating all of the signals in the aromatic region as one signal and getting a total for the aromatic region. So when we look back at the spectrum for phenoxynyl, and we had a signal, a signal, and a signal, all in the aromatic region. I'm never going to give it to you as different integrations for each signal, because what I want you to recognize is that this is the aromatic region. And that just tells me how many hydrogens I have on my aromatic ring. And in this case, it's 3. So I will integrate this entire area as just 3H. And the crazy thing is, maybe each of those signals is 1H, 1H, 1H. But sometimes the signals can be so complicated that they overlap with each other. So you could actually find something that, it's just weird. It can be weird. So to remove some of that messiness in the aromatic region, just integrate that region as one whole. You have questions on integration? In my opinion, integration is one of the most powerful pieces of proton NMR. All right, our last component is called splitting pattern, also referred to as multiplicity. Why does a signal appear as more than one peak? Which, when you think about it, means that one type of hydrogen nuclei is giving off different combinations of frequencies because they're giving different chemical shift, like different ppm values, but they're all coming from one signal. This is probably the hardest part of NMR to even explain. And I don't think that I can really do a good job at it. When you analyze a proton NMR spectrum, 99% of the nuclei are NMR active. 99% are H1, and the other 1% is deuterium, H2. So when you analyze a sample, you're getting 99% of the sample to respond, and you get a very clear signal. But somehow these nuclei communicate about their spins with each other. So statistically, you have the chance of nuclei on one carbon communicating with the nuclei on an adjacent carbon. And when these nuclei are all spin up, these other nuclei have the chance of being all spin up, one spin down, but in different combinations, two spin down but in different combinations, or all spin down. And that gives different signals. Again, I'm not hoping that you understand this, because I'm not sure that I quite do either.
So they're in the same set.
These are one set distinct from this set.
Okay.
One set of hydrogens communicates with its neighbors. A different set of hydrogens. They communicate about their nuclear spin. You remember at the beginning of the semester I mentioned I have a theory that consciousness has no scale? Really? Like your nuclei are communicating to each other and they're not conscious at all? Maybe they're conscious though. Maybe this is a manifestation of nuclear consciousness. I don't know. But what are we without skepticism? You gotta have some imagination to be able to find out the truth. This is splitting pattern. Nuclei communicate with their neighbors and produce different signals. And we have a math equation. The number of peaks is equal to n plus 1. Signals can have peaks. Signals either have one peak or signals have multiple peaks. And the number of peaks is equal to n plus 1, where n equals the number of hydrogens on adjacent carbons. There are some exceptions I want to give you before I give you the rest of the splitting patterns. These exceptions are always singlets. They only have one peak. They do not communicate with their neighbors. That is, the hydrogen of an aldehyde does not communicate with any neighbors on adjacent carbons. The hydrogen of an alcohol, the hydrogen of an amide, an amine, the hydrogen of a carboxylic acid, which you can think of as essentially the same as the hydrogen of an alcohol. Carbon nuclei allow for the communication about spin. Oxygen and nitrogen nuclei do not allow for the communication about spin. Multiplicity is inhibited by oxygen and nitrogen. Multiplicity is facilitated by carbons.
So if you have something bonded, an H bonded to an N or an O or anything other than a carbon,
Yep.
it'd be a singlet?
But anything other than a carbon is generally just oxygen or nitrogen. Maybe a sulfur. But yeah, anything other than, and this is the odd case where it is actually bonded to a carbon.
Yeah, but, okay.
Another exception, but this exception is often more complicated. Hydrogens bonded to alkenes, what we call vinylic hydrogens, and hydrogens bonded to aromatic rings, what we call aryl hydrogens. These are not always as simple as they look. Multiplicity, I would say, is arguably the most powerful tool that NMR offers in structural determination. I have a signal that integrates to 3H. That 3H is probably a methyl group. That signal shows up around 2. The methyl group is adjacent to a functional group. But the signal has multiplicity. Now I know what the group next to it looks like. I can learn information about other groups from a signal. These are the exceptions where we can't really glean all of that information from them. So now I want to look at what does it look like. Let's start with a CH3. If I have a CH3 that is bonded to a CH2, there are two neighboring hydrogens. Notice that these are not the same set. Two neighboring hydrogens, here they are, which means the number of peaks equals 2 plus 1 equals 3. So the signal is what we call a triplet. If that CH3 were adjacent to a CH, n equals 1, number of peaks equals 1 plus 1, 2, we produce a doublet. If the CH3 is adjacent to just a carbon, or even if it's adjacent to an oxygen or a nitrogen, if the number of neighboring hydrogens is 0, then the number of peaks (0 plus 1). Well, it has to have a peak. The hydrogens have to make a signal, so there has to be one peak. It's when neighbors start getting involved that that signal starts splitting into multiple peaks. That we call a singlet.
Because if neighbors aren't getting involved, it's not splitting.
Exactly, there's no splitting with no neighbors. So is that the biggest I can go is 3 peaks? I can only have a maximum of 2 neighbors? Well, the 2 neighbors of the CH3 themselves have 3 neighbors. So 3 neighbors would give how many peaks? Right. Uh, 3 plus 1 equals 4. And we call this a quartet. And to be honest, beyond 4, things just kind of start getting messy. And we start referring to things as multiplets. Notice that CH2 that now has 5 neighbors, which means that it will show up as 6 peaks.
Will there always be symmetry?
You're noticing the symmetry, right? The doublet is nice and clean. The triplet is clean. It actually follows Pascal's triangle, where the peaks in the middle will always be higher than the peaks to their exteriors, and that has something to do with the combinations of splitting patterns, or sorry, the combinations of spins. Like, I can have all of them spin up, I can have 2 spin up, and I can do that 3 different ways. I can have 2 spin down, but I can only do that 2 different ways. Or I can have all spin down. So there's the most combinations of when one is spin up and one is spin down. So there is always that symmetry, except that experimentally, no. Like sometimes you find a doublet that looks like this. It kind of has symmetry, like it's got the 2 peaks, but one is oddly shorter than the other. This can often just be an experimental issue, something to do with the instrument. So you won't always find it. But when you start looking back at these examples, you'll start to see it a little bit more clearly. You'll start to see the shapes that are in here. Okay, can we verify real quick, what is the integration of this triplet? What is the integration of this triplet? How many hydrogens are producing this signal? Yeah, we're looking at the methyl group's signal. And why is it a triplet?
The number of hydrogen on the adjacent carbons.
Because there are 2 neighbors. Not because there are 2 peaks. It's a triplet because there are 3 peaks. Triplet means 3.
Oh, I was
1, 2, 3.
looking at it, no.
It's a triplet because there are 2 neighbors. What's the integration of this doublet? 3H, because we're looking at the same methyl group, but now with different neighbors. Why is it a doublet? Because it only has 1 neighbor. What's the integration of this singlet? 3H. And why is it a singlet? Because it has no neighboring hydrogens. No hydrogens on the adjacent carbons. What's the integration of this quartet?
3H.
Sorry?
3H.
No,
It's 2H.
it's 2H. Because I'm looking at the methylene group, the CH2, which has 3 neighbors. And it's because it has 3 neighbors that it's a quartet. 2H. What's the integration of this sextet? 2H. And why is it a sextet?
That's 5 neighbors.
It's got 3 neighbors on one side and 2 neighbors on the other. So it's got 5 neighbors, but it integrates to 2H. Here's a question. Which of these 3H signals would you expect to be the tallest on an NMR spectrum?
I think it's the bottom one, singlet.
Why? It's the skinniest.
Yes.
It's not spread out across multiple peaks, but it has to have the same area. So if it's not making up that area in width, it has to make up that area in height. The widest because it has the most peaks, the tallest because it has the least peaks, all the same area. Great.
Because they're all 3.
Because they're all 3H. Fun stuff, right?
But a 3H singlet compared to like a more H triplet or doublet, that doesn't stand. They have to have the same area for it to be the tallest.
Yeah. Like I'm not going to compare this triplet to this quartet because they have different areas anyways. All right, let's look at this spectrum for ethyl acetate, which is a fairly common solvent. Those of you that were in my lab this semester, we experimented with ethyl acetate as using it for a different solvent. Here's 4 ppm to 1. I'd like you guys in groups to assign integration values to these 3 signals. To be able to do that, you have to know which hydrogens are producing what signals. To be able to do that, leverage their chemical shift and their splitting pattern.
I think the one furthest to the
Evelyn, you can join this group. You're close enough.
methyl group furthest to the right.
Okay. So are we?
Yep.
We have
We're gonna
3
assign integration values to those signals based on what we understand from Sam, have you seen those animations where people take cartoon characters and condense them into like one color per pixel based on their outfits? That's what your earrings are kind of giving. I'm like,
It's my roommate got them for me. They're made out of old surfboards.
really?
So
Yeah, she's from
it's
That's very cool.
1, 3,
2H
H, it's,
and the 4 would be 3H.
So would it be safe to assume that
Yes,
number
because
is
it is.
So what about the most
so 3H,
Well, number of peaks is n plus 1. If you want to find n,
it's like the number of
Is that gonna be
There you
the 4 or the 2? Or would the carbon attached to the?
so tell me which signal you're
Does
looking
that
at.
little bond
Yeah,
be the
for this left, 4 peaks must have 3 neighbors. Yeah.
Okay,
And do you have any
carbon attached to
hydrogens
the
in your molecule that have?
So the one furthest to the left. What would that be for, 2, do you think?
and neighbors.
Because this one has,
because this one has 1, 2 neighbors.
Well, carbons don't show up on proton signals. We only see hydrogen signals. We don't see carbons. So like that carbon is irrelevant.
I thought we were like,
yeah,
we got it.
Because we talk about hydrogen.
He's like, sit in.
And there are how many hydrogens on the carbon?
Yeah,
So, the singlets are the guys that have no neighbors, no neighboring hydrogens. So our CH3 on the left doesn't have any hydrogens, so we need to the right of it or to the left of it. So that's how that's the singlet.
Good.
3H.
Sorry,
Okay.
We're thinking.
No hydrogens on that carbon, which means these 3 have some neighbors.
3 neighbors to the side.
What signal will you
Plus
see?
1.
So far.
So let's see. Sorry, what number of peaks will you see in the signal?
Oh, there's, because there's,
Good.
no, that's these 3 hydrogens.
See
Neighboring
like
hydrogens.
singlet?
Yeah, so CH2 has
Okay.
those 3
So
next to it.
maybe we have confirmation.
Well, no, this has 1. Yeah.
Right.
I was confused about that. I was like, neighbors of what?
So still we're looking for hydrogens that have
Or
some
it's
neighbors.
gonna be to this
Here.
this.
Are we supposed to do all of them? Just for fun. Okay.
Oh, that's an oxygen.
This one has
It's not, and remember, we're looking for. I'm gonna let you and Roland finish this, because Roland's got it. So you can kind of test your reasoning off him.
So this is CH3.
Yes, it is. Great work. How do you feel? So you can do the next one?
That's what we're looking
Yeah, but
Although the next one's not as,
I was like, I can't tell if it's 2 peaks here or 3.
I'd go to the one after that.
Okay.
Go to the far right one.
It's like,
You guys got it?
Alright, so we got CH2, that's CH2.
Yeah.
Great, great.
So.
The only thing that I would change is to put the coefficient in front and call it 2H, 3H. So it doesn't come across
I think it
as
is.
H2 or H3, like a molecule.
Yeah, I love
This is
green here.
all
So,
from-
yeah.
So then this will be with the.
Okay, so then that, because there's,
Yep.
how many are there?
Yep.
There's
Exactly.
No, I
This
don't know
one
if
would
you
be
would call this four separate peaks.
Yeah.
Like,
Yes,
to
it
me,
is.
these just seem like maybe it's hydrogens doing like local
Perfect.
stuff. And but this is the
You guys got it?
thing. I don't know, well, obviously, this
Um,
is getting there.
Oh, you're doing it on.
I am confused about
Oh,
this.
it's both. I put it on both sides,
This
so actually it's
two,
here as well.
two neighbors.
Under splitting patterns. Yep. But
Very nice.
either way, very organized. I duplicated them. So where are you guys at? What are you thinking?
Which one was our other CH?
Do you know which one that belongs to?
That would be the single of
How far do we go? Like,
Carbon-
the CH
the carbon-
has
well,
one
carbonyl
CH
carbon
here. Do we count
Doesn't
it?
show up because only hydrogens show up.
Right, yes.
So it's the
It's like,
methyl
this is the
hydrogens.
CH3,
Uh-huh.
this,
Over the
right?
left.
Now it has
Because they
these
have
two
no
neighbors.
hydrogens.
Do you count those two?
No.
No,
It's just
adjacent.
This one is,
Yeah.
you'll,
This one's come up. Okay,
Good.
so that guy.
So the
is
chemical
five
shift
neighbors.
helps
That
you.
guy's gonna be six.
And did the splitting
That
pattern
guy's a
confirm?
multiply.
yeah, so that
That's
has,
2H.
So that's
Three
probably
neighbors
this
right
one.
here, so it's got.
Which one are you calling a multiply? This one?
Perfect.
The middle one?
You nailed it. All right, so I want to go through this one together because I saw you guys leverage all of the information given to you. First, splitting pattern. I have a CH3 that has no neighbors. It's important to remember that we do not see signals from carbon here. We only see signals from hydrogens. And these hydrogens have no neighboring hydrogens. So they should show up as a singlet 3H. Now I only have it one singlet, but I can also leverage chemical shift. This methyl group is adjacent to a carbonyl, and according to the correlation table, being adjacent to the carbonyl puts you on the right-hand side, the more shielded side of the functional group adjacent, so closer to 2. Hey, close to 2, I have a singlet that must integrate to 3H. Another way that you could label this, you could call these A, and then call this A, although I'll be honest, I actually prefer to call them A, B, C from the spectrum, which means I would come back here and label this as B. And in lab next week, that's how I'm going to encourage you to do it as well. Now I've got another 3H. And I know that 3H has 2 neighbors, so it should show up as a triplet, 2 plus 1. And it's furthest away from the functional groups, so it should be the furthest to the right. Furthest to the right, I have a triplet, must be a 3H. That is group C. And then lastly, I have a 2H with 3 neighbors, that's a quartet, directly next to an oxygen, which shifts you further left than being directly next to a carbonyl, closer proximity to the electronegative atom. Furthest left is that carbonyl. Is that 2H. Here is A.
This is how you would have us label it on the midterm?
You don't have to do a lot of this on the midterm. All of your questions are multiple choice about this. Yeah, so I'm not going to have you guys mark up an NMR spectrum for points. Just know how to interpret them to answer multiple choice questions. Any other questions?
Can we go over A again?
A 2H group adjacent to 3 neighbors. So I should see a signal of 4 peaks.
Okay.
One thing I saw Sammy doing back there was, one of the first things that she did was label how many neighbors these groups have. Which is a great idea because actually you can start building it backwards too. If you know that the integration here is 3H, if you know that's a CH3, and it is a triplet, then I know that it has 2 neighbors. And I should be able to find 2 neighbors somewhere else that have at least a quartet, if not more. So you can use this information to build the molecule. Okay, the spectrum that you see just to your right, I want you to think of this as 1,4 di-substituted benzene. We also refer to this as para. And I told you guys that aryl hydrogens can be quite complicated sometimes, but it turns out when you have a 1,4 di-substituted group, you get these two nice doublets, just like you'd expect, because your aromatic ring has two sets of symmetric hydrogens, each with one neighbor. So those two signals get split into doublets and become integrated as 2,2. That is the only time that an aromatic region is nice and easy to analyze and integrate. Is if it's symmetric di-substituted. So we could integrate this as 2H, 2H, but as you guys saw earlier, we can integrate it as just 4H. And the clean splitting tells us it's di-substituted. What's the integration to the right of that third signal on the right? It's the alcohol's hydrogen, so it's 1H. All right, that structure on the far right, methyl propyl ether.
And we would think an OH would be far to the left, but because it's OH, it's further to the right than we expect.
Yes, you'd think that the oxygen would shift that signal super far left, like it does on the carboxylic acid, but it doesn't. It actually leaves it a lot further right than you might expect, further right than the aromatic region. All right, methyl propyl ether, which gives a signal that looks like this. Can we assign these integration values? Here's 3, and here's 1. What's the first thing that you're looking for? When you look at that molecule and you look at its spectrum, where does your mind go first?
I think, is that a singlet right there, or is that?
Is that a singlet or is it a really weird triplet? Could it be both?
I think it has to be both because there's not enough peaks for how many groups you expect.
How many unique sets of hydrogens did we see in ethyl acetate? We saw 3 sets of hydrogens, 1, 2, 3, and we saw 3 signals, 1, 2, 3. How many sets of hydrogens do you see here? Yeah, 1, 2, 3, 4, and you only see 3 signals. So 2 of them must be overlapped.
Yeah.
How do I know which 2? We're gonna have to figure it out. Let's use some splitting pattern first. Okay, and chemical shift. Furthest to the right means most alkane. Yeah. The most alkane type region. And how many neighbors?
2.
2 neighbors, because the signal is a triplet.
Should be the furthest.
The furthest methyl group on the left. All right, once again, I'm going to call this A, B, and C. And I'm going to say this is C. This must be 3H. What about the second most alkane type region? How many neighbors does it have? A lot.
5.
Maybe 5? Yeah, if there's 6 peaks in there, then it has 5 neighbors.
So it's the second. Should be the second carbon.
Only this has 5 neighbors. Nothing else in the molecule has that many neighbors. because the other CH2 only has 2 neighbors, which would split as a triplet. But the proximity to the oxygen says it should shift further to the left. It should be a triplet shifted further to the left because of its proximity to oxygen. Well, here's a triplet that is shifted further to the left, but if I integrate this, I do not believe I'm going to get 2H. Because I also don't have a signal for my methyl group. So when I integrate this, I actually end up integrating 5H because my groups overlapped with each other. And by God, could they have overlapped any better? Not at all. The fact that the singlet from the CH3 sat right dead center on the triplet is so coincidental. Are we saying that the CH3 on the right of the oxygen and the CH2 on the left of the oxygen are the same? That they're chemically equivalent? Not at all. It is just coincidental.
So we would write 5H instead of like 2H plus 3H, right? Or
Yeah, you could write 2H plus 3H. That's not a bad way to do it. But if you were to get in here with the software would only be able to integrate them together because they're together. And actually that's not true because the software has gotten very good at being able to pull apart different peaks that have overlapped with each other. This is amazing that they've overlapped dead on with each other. A lot of the overlaps are more like offset overlaps. So one peak is overlapped with one peak, and then you just kind of get this weird mix. And obviously people care a lot about this instrumentation, this analysis method. So they've devised the tools to be able to separate them.
Would it be easier to think of that as like A1 and A2?
You could call it A1 and A2.
Okay, kind of different, but they're affiliated in the same, encapsulated as the same H.
The website where I get all of these spectra is called SDBS. It's the Japanese Spectral Database. And it's linked on your external resources for the course. And in lab, you guys will be sent to use this resource. When they have a spectrum like this, they actually do this. They label their signals from left to right, and then they assign them to the structure. And they will actually go in and tell you that these are 2 different signals. They'll label it as A, B, C, D. And the distinction, they'll have like 3.11 is A, and 3.09 is B. So to the naked eye, you can't tell the difference between 3.11 and 3.09. But they know, calculations and experimental evidence proves, they know that they've got 2 different sets. Fun stuff, right? Crazy. All right, so piecing it all together, we've already kind of worked on this, assigning things to their structures. I don't like these next 2. They're a little too complicated. And we've basically just done this. You can see how crazy cholesterol is. And you can see how much alkane region there is. So when assigning cholesterol, you might not be able to assign every single peaks, but you could assign specific peaks. For instance, cholesterol has 1 vinylic hydrogen. Do you see the 1 hydrogen bonded to the alkene carbon? It's on the bottom. So I should expect to see something in the vinylic region. Oh, I do, 5.4 ppm. I see a vinylic hydrogen. I can assign that hydrogen to its spectrum. Even if I can't assign anything else because it's too cluttered, I can at least find a unique thing to assign. Then with our methyl vinyl ether, I can assign the CH3 from the methyl because it shows up as a nice clean singlet. But then all of the other vinylic hydrogens, look at how messy they got. Are those doublets? Why do they look like that? They're so short and wide. It gets complicated. Remember, those vanillic hydrogens don't always behave the way you'd expect. Also, look at that one signal on methyl vinyl ether. That looks like it's in the aromatic region. According to our correlation table, 6.5 is where our aromatics pretty much start. That's the hydrogen that is both vanillic and adjacent to the oxygen. It has this compounding effect on its chemical shift. All right, the last one, I think I want to come back and solve these with you guys another day. I want to wrap up with something different, but the idea here is to take the chemical formula and devise a structure based on the NMR spectrum. It's almost impossible to do if you don't have a chemical formula, but with a chemical formula, it's a lot easier to do. So, I want to take us on a slight detour. This has been proton NMR.
This is good job.
Thank you. You too. Which, remember, proton is the hydrogen nucleus. So proton NMR is analyzing H1. Okay, start carbon NMR, which is referred to as C13. You know, it's actually kind of funny. We call it C13, but it reads 13C because isotopic numbers always go on the top left. But we read it as C13. Carbon NMR is far less detailed than proton NMR, but shares very similar properties. So first, equivalent sets. All the same. When you look at a carbon structure, you can assign carbons as either the same carbon because they're symmetric to each other, or distinct carbons because they're distinct from each other. The only difference is that you don't get these clusters of carbons like you get clusters of hydrogens. You're not going to have some C3 group like you have a CH3 group. This is all the same. Chemical shift. Very much the same. The difference, and again, I uploaded this new version of the correlation tables to Canvas, and I can pass this around if you guys would like. Otherwise, I think actually I'll just encourage you to look it up. Here's our proton NMR on top, broad bird's eye view of proton NMR. Just underneath it is carbon NMR. Broad overview. You know what's on the furthest right? Alkane carbons. Then carbons adjacent to heteroatoms, alkyne carbons, nitrile carbons, alkene carbons, aromatic carbons, and then carbonyl carbons. So once again, the closer you are to those functional groups, especially the carbonyls, the further left the signal goes, because it's the same shielding and de-shielding situation. So chemical shift is all the same. Integration. You won't see it. We don't integrate carbon NMR. And I don't know why. It's still kind of a weird thing. Carbons do really weird things though, because their nuclei are nothing like the nuclei of hydrogens. So carbons, we can do NMR studies on them where CH2 carbons don't show up. They don't give any signal. And methyl carbons go straight up, but CH carbons go straight down. And somebody watches this on the internet and they'll probably tell me I'm wrong, because I might be lying. I don't know. I am saying this a little bit out of my ass because it's weird what carbon NMR does. But there are types of carbon NMR where you can distinguish CH3 carbons from CH2 carbons from CH carbons, and I think maybe from carbonyl carbons because of whether they go up, down, or don't show up at all. So there's different ways that you can analyze carbon NMR, but we don't integrate them. You'll never see a carbon NMR that has 1C, 5C, 3C written on it. You'll never see it. And oddly enough, you can't really go by height either, because sometimes the same number of carbons are producing signals and they just have different heights because they're giving off different intensity of signal. It's weird stuff. Splitting pattern. You won't see it. Hydrogen nuclei communicate through their covalent bonds between their carbons. Hydrogen nuclei communicate about their spin states and the combinations of their spin states. Carbon nuclei do not. So there is no splitting pattern. Carbon NMR is just a series of straight lines. That's just a random. Their chemical shift is much broader, by the way. It goes from about 10 ppm to about a 220 ppm. Very high frequency range. Also, 99% of protons are NMR active. 99% of hydrogen nuclei are the isotope that is NMR active, but only 0.1%, I think I have that backwards, 1.1% of carbon nuclei are NMR active. So when you analyze a sample for its carbon NMR, you often have to run very long scans, because for every 100 molecules, for every 100 carbon atoms, only one carbon is there actually responding to the NMR and giving off a signal. So you have to take more scans, longer scans, to try and pick up enough detail from it to get a nice clean spectrum. Carbon NMR has gotten a lot better in the years. Our NMR in the lab at Salt Lake Community College can run carbon NMR in a few minutes. When I was in graduate school, I asked to run a carbon NMR of one of my synthesis products, and my advisor suggested we not do it because of how expensive it was to run. We had to pay for time on the NMR and for how long we were going to have to run it. She just said it's just not meaningful for you to run that carbon NMR. So this is the first time I've ever given carbon NMR before, and this is all I'm going to give on it. Because it's not that common, but it's not impossible that you'll see it going forward. You might see it in the MCAT prep. I've had students come back preparing for the dental exam, the DAT, told me that it's touched on in there too. This is all you need to know about it. So if you can master proton NMR, carbon NMR is much more of a breeze. You just need to know equivalent sets show up differently and they show up based on their chemical shift. But it's not really feasible to integrate them and they won't give any sort of splitting pattern. All of that, a day and a half on NMR, proton NMR, and 8 minutes on carbon NMR.
On our exam, will we have like the correlation tables?
You will have some, and you'll have versions of them. I encourage you to look at the practice midterm, because those are the tables I'll give. We're going to talk about IR tomorrow, and you'll get most of the IR, just not the structures.
But like
You will only get the proton NMR, not the mass spec and not the carbon NMR, and it won't have any words. It will have only the structures.
Okay.
So take a look at, I know that's a little confusing to say, take a look at the practice midterm before you come in for the midterm, so you know what your tool will be. It's important that you know how to use your tool. The rest of the time is yours. I'll see you guys tomorrow for some practice on structure and IR.
Why can't we figure this out?
Like so
You are too, you're not hydrated. I would love to.
Oh no.
There's
Because it's